Hi there, this is Jagdish Prajapati from Kutch, India. I am going to present on use of hybrid LSTM model to predict SST over the Kutch region. So, without wasting time, let us start with the introduction. As we know, SST is a most widely used ocean variable. It influences ocean dynamics, weather forecasting, and atmospheric analysis. It also improves regional forecast and global analysis through data assimilation. It is also useful for identifying potential fishing zone and for detecting marine heat waves. So, considering all the above importance of SST and the research gap found through the literature survey, we have identified the following objectives. Can a forecast from a hybrid ML model outperform SST analysis? Can the hybrid model predict fine scale SST fronts? Can the model predict high frequency 3-hour SST variability? How does the model perform during extreme events? Is it reliable for producing marine heat wave forecast? So to address the above objective, we identified Kutch region for our study as a test bed. We used OSTIA level for daily SST from 2012 to 2021, which is a gap-free graded sea surface temperature analysis from satellite and in situ data with an accuracy of minus 0.09 degrees centigrade. To answer the above question, we have designed a hybrid model. This hybrid model is shown here. This is the flowchart of the hybrid model. We first decompose the SST into 5 IMFs. You can see here using the BMD, and then use the last 25 IMF value and feed it into the LSTM model to get prediction for each IMF. To get the complete prediction, we add the 5 prediction from the IMFs. This is procedure at a single grid point. Now to get the regional map of SST over the domain, we have to reiterate the same procedure over all grid point of the Indian domain. Now to assess the quality of the model, we have shown the following analysis. Red color here shows the RMSC and blue color shows the correlation with respect to the lead times. Here the straight red line and the horizontal blue line shows RMSC and correlation respectively for the glories. During 2020 and 2021, the domain average correlation coefficient for glories over the study area is lower than the 7th day prediction correlation of the hybrid model. Similarly, the RMSC is higher in glories and the RMSC for 7th day prediction is lower in the hybrid model. Thus, we found that for the larger scale, the hybrid model is superior in comparison to the glories. The probability density plot here demonstrates that the most probable RMSC of the predicted SST is smaller than the most probable RMSC of the glories SST. That is, the hybrid model manages to forecast a more accurate SST over most of the region compared to the SST reanalysis with a lead time of 3 days. There are more locations showing higher correlation in the hybrid model compared to the glories. This plot suggests that the third day predicted SST from the hybrid model is outperform model outperforms the SST reanalysis from glories at both finer and coarser spatial scale. To further analyze, we show here correlation and RMSE for hybrid model, correlation and RMSE for glories, and their differences here. It is evident that the hybrid model SST demonstrates higher correlation and a lower RMSE across most of the domain, particularly close to the coast, except over a region near the southern boundary of the domain here. The overall the hybrid model appears to fare better. However, we would like to alert the readers or the audience here that the Pearson correlation coefficient is not a general measure of dependency, and therefore one must dig deeper before assessing the supremacy of the predictive skill of the models. So to further analyze, we have shown here the marginal probability graph for OSTIA black color, hybrid model in red color, and for glories it is in blue color. The most probable SST in OSTIA lies in the range between 28 to 30 degrees centigrade, which is a feature reasonably reproduced by both the hybrid model and glories. Even though both the hybrid model and glories replicate the qualitative feature of the observed SST probability density, however, glories generates a spurious high density for SST at 28 degrees centigrade and 30 degrees centigrade here. From another statistical perspective, we computed KL divergence. Here KL divergence value for hybrid model is lower in comparison to glories. That shows the good alignment with observation, and the symmetric uncertainty value is higher for hybrid model. That shows the enhanced prediction skill of hybrid model in comparison to glories. To further check the reliability of the hybrid model, we have shown here the conditional probability distribution of observation with the given hybrid model and glories. Glories do not produce forecast, but we assume glories to represent the upper bound of predictive skill of forecast of any dynamical system. In both the cases, you can see that the highest density regions align along the diagonal, indicating a strong correlation between forecast and observation. However, notable differences in their probability distribution can be seen. The hybrid model exhibits a sharper and more concentrated probability distribution along the diagonal, suggesting that it provides more reliable and less dispersed prediction of OSTI SST. In contrast, glories figure here shows a broader spread for a lower range of temperature, indicating greater uncertainty in its prediction. The same is also confirmed with the conditional probability at a particular temperature, 30 degrees centigrade here and 20 degrees centigrade here. These findings suggest that the hybrid model provides a very reliable forecast that outsmarts the hybrid gas from one of the best state-of-the-art reanalysis. Now it is time to check the applicability of the hybrid model for different applications. In this graph, you can see that we have shown here the SST fronts using that was derived using CCA algorithm. Here you can see that the hybrid model which is in red color, is mostly aligned with the observed sea surface temperature front in black color. However, glories generate some spurious fronts here, here, and here also, which is not evidence in the observation. So, the hybrid model manages to forecast the small scale behavior of SST with a lead time of 3 days. To further check the applicability of model at a buoy location for producing high frequency SST, we have shown here the temperature series from buoy in black color, hybrid model red color, and our dynamical model IO hubs in blue color. Here also you can find that the hybrid model is performing best, and therefore it is able to generate high frequency SST at a buoy location. However, I have not shown here the graph for assessment during the cyclonic storm, but at a result we found that the model is not able to capture SST variability during a storm condition. To further check the applicability of the marine heat wave, I have shown here a plot for the detected marine heat wave. This is for observation and this is for hybrid model. This is for glories. The red shaded part here shows the detected marine heat waves. The predicted marine heat waves are mostly aligned with reasonably good accuracy with a lead time of 3 days. In contrast, glories estimate a single marine heat wave event during 2020 and therefore fails to delineate the multiple marine heat waves that are observed during this period. This reflects a persistently warm SST in glories at this location. In short, the hybrid model manages to predict the pronounced marine heat waves with a reasonable certainty with a lead time of 3 days. So, to further summarize this study, I have listed some points in the conclusion and future recommendation section. So, the study focuses on SST forecasting over a small domain but can be extended to the entire Indian Ocean. Predicted SST outperforms state-of-the-art numerical model with data assimilation. The hybrid model accurately predicts SST fronts with a lead time of 3 days. The model effectively predicts high frequency SST signals with a lead time of 1 day during normal conditions. However, the model shows limitation to produce high frequency SST during a storm condition. High resolution like 3-hour or 6-hour synthetic SST can enhance atmospheric model forecast. Now, I am very thankful to Director Request for approving my trip. Funding support received from Ministry of Earth Sciences and also the funding supports for this travel received from Copernicus UMedSec. I am also thankful for the GHRSST project office for all kind of support. These are some differences used to prepare this poster. Thank you.